Welcome back to Calculus for Economics. Today is Thursday, March 26th, and we're going to talk about a new topic today, exponential and logarithmic functions. Exponential functions are most familiar to us, and so we'll start there. The basic idea for exponential functions is, well, we've already had some experience in terms of using exponents, so why don't we think about functions that can be defined that way? So here's a couple of examples. Suppose we have a function f of x that's equal to 2 raised to the x power. That would be an exponential function. Another example would be g of t, which would 0.3 raised to the t power. So the idea in an exponential function is that the base is a constant and the exponent is a variable. So you should contrast that to a function like x squared, for instance. Even though it has an exponential in it, it's not an exponential function because in y equals x squared, x is the base and that's the variable. Whereas in a truly exponential function, the base is not a variable, it's a constant, but the exponent is a variable. And so the general definition would be f of x is some constant, which I'll call b, raised to the x power. And here we're going to assume that the base b is bigger than 0 and it's also not equal to 1. And the reason for that is, first of all, if b were negative, like say negative 1, then you might run into problems if the exponent x is something like, say, a half. Then you've got negative 1 to the 1/2 power. That's the square root of negative 1, which isn't even defined. And also, we assume b is different than 1 because 1 to any power is just 1, and that's just, so that would be a very uninteresting function. 1 to the x is just going to always be equal to 1 no matter what x is. So let's take a look at these functions. First, we'll start with their graphs. Here you have the graph on the left of an exponential function b to the x, where b is bigger than 1. So we see that the function is increasing. Of course, when x equals 0, b to the 0 power is 1, and that's because b to anything to the 0 power is 1. And we see that the function is increasing. On the right, you see the graph of b to the x, where b is between 0 and 1. And now it sort of reverses. Now it's a decreasing function. Of course, when x equals 0, you still get f of 0, b to the 0 is 1, because again, anything to the 0 power is 1. But now we have a decreasing function. So these functions have a couple of properties, the graphs do. First of all, the graph is always positive, so it's always above the x-axis. If b is bigger than 1, you actually have a horizontal asymptote here at the x-axis. So it's the graph, as you keep going to the left, the graph gets closer and closer to the x-axis, but never actually gets there, never touches it. And then as you go to the right, in this case, the graph just starts increasing ever more quickly. In fact, the rate of increase of exponential functions is something that we'll pay special attention to. That's where we get the commonly heard phrase exponential growth, as in the coronavirus pandemic is growing exponentially. That is a metaphor for extremely fast growth, and exponential functions do have that. And so that rate of increase there is very high for exponential functions when the base is bigger than 1. When the base is less than 1, things kind of reverse. The horizontal asymptote is now out to the right, so if you continued the graph here out to the right, it would get closer and closer to the x-axis. And the exponential growth actually occurs in the left part of the graph here. By far the most common situation is when the base is bigger than 1, and usually that'll be the situation we'll be dealing with. Some basic properties of exponential functions next. First of all, the domain of an exponential function is minus infinity to infinity, so they're defined for all values of x. The range of an exponential function is always going to be from 0 to infinity, so b to the x is always going to be at least 0. You'll never have negative values in the range of an exponential function. Some of the other properties are just basic properties of exponents, and I'm just writing them now with variables as the exponents. But these are all properties you should be familiar with. The additive property b to the x plus y is b to the x times b to the y. Subtractive property b to the x minus y is b to the x over b to the y. Of course, b to the 0 is 1. B to the negative x is 1 over b to the x. All these are just normal properties of exponents that we've used before. There is one other property that I'd like to highlight, though, and that's when you've got two exponential expressions with the same base and possibly different exponents. Well, if those two expressions are equal, if b to the x equals b to the y, then it has to be the case, and this is just my symbol for if and only if, the two exponents are equal. So x would have to equal y here. So here's a little example of that property in action. Suppose you were asked to solve an equation like this. A b times b to the 3x minus 2 equals the quantity b raised to the x minus 1 squared. Suppose we wanted to solve that for x. Well, the first thing to do is to sort of write everything in terms of exponents. So b I can just write as b to the first power times b to the 3x minus 2. And then over here on the right hand side, what I've done is I've used that property that says b to the x raised to the y is the same as b to the x times y. So that's what you see here. B to the x minus 1 squared is the same as b to the power x minus 1 times 2. Now going to the next step, b to a power times b to a different power, you just add the powers. So b to the first times b to the 3x minus 2 is b to the 1 plus 3x minus 2, and that's just 3x minus 1. And then on the right hand side, I've just multiplied out in the exponent there to get b raised to the 2x minus 2. And now we have the same base and different powers, but the two exponential expressions are equal. So that means the two exponents have to be equal. So 3x minus 1 has to be 2x minus 2. And now I can just solve that for x. I'll bring the 2x over here and the 1 over here, so I just get x equal negative 1 as the solution for that equation. So that's just using those basic properties of exponents. There's a special base that we're going to work more and more with as things go along, but let me just go ahead and mention it now. It's this base that's given the name e. The e is an actual number. It's got a kind of a strange definition. E is the limit as x goes to infinity of this exponential type function, 1 plus 1 over x, all raised to the x power. And it turns out that that limit actually has a definite value. It's 2.71828.182, and actually there's lots more digits after that. It's an irrational number. The decimal never repeats or terminates. This is called the base of the natural exponential function. So the natural exponential function is just an exponential function where the base is this number e. You may ask, why do we call this the natural exponential function? It doesn't look very natural just on the face of it. Well, it turns out to have nice properties from a calculus point of view, and we'll be getting into those in a subsequent lecture. Let's look at an example with the natural exponential function. Suppose we wanted to solve this equation, e to the x squared minus 3x plus 2 equals 1 for x. Well, given what we know right now, we need to write 1 as some power of e. Of course, that would be the 0th power, because e to the 0 power is 1, just like anything to the 0th power is 1. And now, again, we've got two exponential expressions that are equal, same base, and so the exponents have to be equal. So I get x squared minus 3x plus 2 is 0. Now that's a quadratic equation, and this one actually factors pretty easily into just x minus 2 times x minus 1 equals 0, and therefore x has to be either 2 or 1. So our solutions are x equals 2 and x equals 1. Next, let's take a look at logarithmic functions. These are actually related to exponential functions in a very fundamental way. They're basically inverse functions for exponential functions. So let me try to show you what I mean by this. Let me first, let me see if I can do this way. Here on the left-hand side of the paper, I've written down several exponential expressions. 2 to the 3rd power is 8. 6 to the 5th power is 7,776. 3 to the negative 2 power is 1/9. Those are all real basic. Each one of them has an equivalent expression in terms of what we call logarithms. So 2 cubed is equal to 8. How we express that in logs is we would say that the log to the base 2 of 8 is equal to 3. So log base 2 of 8 equals 3 means the same thing as saying 2 cubed equals 8. So in other words, log base 2 of 8 is just the exponent you need to raise 2 to get 8 as the result. In the same way, 6 to the 5th equals 7,776 would be, in the language of logarithms, we would say log, what base? The base is 6, of 7776 would equal 5. So in a sense, the log base 6 is telling you the exponent you need to get whatever number you're taking the log of when your base is 6. And in the same way, 3 to the negative 2 equal 1/9 would mean what? It would mean log base 3 of 1/9 equals negative 2. So logarithmic functions are the inverse functions for exponential functions. And the general definition is very much like those examples. Log base b of x equals y if and only if b to the y equals x. So the way to think about this is that log base b of x is the exponent when x is expressed as a power of b, right? So to find log base b of x, you write x as a power of b, and whatever that power is, that's the value of log base b. So that's really just the same thing we said on the previous slide, stated in a little bit more general way. Here are the graphs of the logarithmic functions. Here again, there's a distinction between when the base is bigger than 1 versus when the base is between 0 and 1. When the base is bigger than 1, you again have this increasing function. Now, instead of a horizontal asymptote, which we had for exponential functions, we've got a vertical asymptote at the y-axis here. And the function's increasing, and the x-intercept is now 1 instead of the y-intercept being 1. So log base b of 1 is always equal to 0 no matter what the base is. The graph does increase. There's no horizontal asymptote for a log function. It keeps on increasing, although the rate of increase is really slow. And this is kind of the opposite of exponential functions. But if the base b is between 0 and 1, again, the situation kind of reverses. You still have a vertical asymptote at the y-axis, but now the graph goes up the asymptote instead of down. You still have an x-intercept of 1, but the graph now is decreasing. And again, there's no horizontal asymptote for this function, but this decrease continues to happen, but again at a very slow rate. Next, let's look at basic properties of logarithmic functions. The situation here kind of reverses from the exponential functions. Now, the domain of a log function is from 0 to infinity. So you can't take the logarithm of a negative number. That's one consequence of this. And the range of a logarithmic function is from minus infinity to infinity. The next few properties are really analogs of the corresponding exponential properties. The log base b of a product, x times y, is just the sum of the individual logs. So that's the analog of the exponential property that b to the x times b to the y is b to the x plus y. For logarithms, it turns out that the log of x times y is log base b of x plus the log base b of y. It's kind of an analogous rule for quotients. Log base b of x over y is log base b of x minus log base b of y. And then this rule, log base b of x to a power, turns out to be the power times the log base b of x. And again, there's a kind of a similar rule to the last one for exponentials. If you've got the same base for a logarithm and log base b of x equals log base b of y, then that tells you that x had to be equal to y. So it shouldn't be surprising that since logs and exponentials are so related, there's several ways to express that relationship. This is just the definition that we had on the previous slide for the logarithmic function base b. Log base b of x equals y means the same as b to the y equaling x. But if you work with that a little bit, you can get some interesting inverse function relationships. If you take log base b of b to some power, well, you just get that power back. So it's like log base b undoes whatever raising b to the y power does to give you back just y. And that's easy to see from our first expression here, right? If b to the y equals x, then just plug that in here, log base b of x, but x is b to the y, so log base b of b to the y equals y, and that's exactly what we're saying here. And that would be true for any y. And you can do it the other way too. If y equals log base b of x, then b to the y equals x, but plug in what y is. Y is log base b of x. So b to the log base b of x is just going to be x. So one way to think about this is kind of the log function base b and the exponential function base b basically just sort of undo each other. Each one does the opposite of what the others did. If log base b turns x into y, then b, the exponential function, turns y back into x. And so these are called the inverse function relations. Recall we had that special base for the exponentials, the number e, that was 2.71828, the base of the natural log exponential system. The corresponding log is called the natural logarithm, and it has a special notation. Ln of x stands for the natural log of x. It's just the same as log base e of x. And it has that inverse relationship with the natural exponential. Natural log of x equals y if and only if e to the y equals x. And so one thing that comes out of all this is that any logarithm can be written in terms of the natural logarithm. So let's look at an example there. suppose you wanted to find log base 2 of 10. Well, it would be a natural thing to do would be to go to your calculator and say, well, let's see, where is my log base 2 function? And on most calculators, there's not one. But there is a natural log function on any scientific calculator. On our TI-84, the natural log function is right under the common log function. The common log is log base 10. But if you've got a natural log function, then you can use it to find logs to any base. So let me show you how that works. First of all, we don't know the answer yet, so let's just call the answer, whatever it is, y. So log base 2 of 10, let's just call that answer y. And then let's use the definition of the logarithm to write that as 10 equal to 2 to the y. So this is just using the definition of the log base 2. Log base 2 of 10 is the exponent you need to raise 2 to in order to get 10. So 2 to the y would have to be 10. Now take the natural log of both sides of that equation. So you get natural log of 10 equals natural log of 2 to the y. And then use that property that says that the log of something to a power is the power times the log of the something. So natural log of 2 to the y is just y times natural log of 2. That's using one of those basic properties that we discussed earlier. And now I can just solve this equation for y. If I divide both sides here by natural log of 2, I get y is the natural log of 10 divided by the natural log of 2. And so, of course, what was y? Y was log base 2 of 10. So log base 2 of 10 has to be natural log of 10 over natural log of 2. And that turns out to be about 3.322. The way I got that is I just used my natural log key on my calculator. Let's see if I can do this. So I would say natural log of 10 divided by natural log of 2. And can you see that? There it is. And that's the 3.32192895, etc. that we just saw. So in general, this is true for any logarithm. There is a change of base formula that expresses any log, a log to any base, in terms of the natural log. And it's just the same as what we just basically saw. Log base b of x is just the natural log of x divided by the natural log of b. There actually is a corresponding change of base formula for exponentials. You can write any exponential in terms of the natural exponential, and here's that. Not going to focus on that too much for right now, but we will need it a little later as we work more with exponentials and logs. So just wanted to kind of get that out there. Here's a final example, one that we really couldn't have done at the start of the lecture because it has this complication. I've got two exponential expressions, but the bases are different now. So 3 to the x equals 2 to the x minus 4, and I want to solve that for x. I can't just say that x equals x minus 4 here because I can't equate the exponents, in other words, because the bases are different. So how could we solve this guy? Well, one method would be to use the natural log. So all I'm going to do is take the natural log of both sides of my equation. So natural log of 3x equals natural log of 2 raised to the x minus 4 power. And then let's use the property that natural log of a power is the power times the natural log. So natural log of 3 to the x would be x times natural log of 3. And natural log of 2 to the x minus 4 would be x minus 4 times natural log of 2. And then I'm just going to multiply out this right-hand side here to get x times natural log of 2 minus 4 times natural log of 2. And then, looking at the left and right-hand sides now, I want to collect the terms involving x. So I'm going to bring this guy over to the left-hand side by subtracting. So we'll say x to the natural log of 3 minus x times natural log of 2 equals, and we still have negative 4 natural log of 2 on the right hand, on the right hand side. Now factor out the x from the left hand side, so you'd get x times natural log of 3 minus natural log of 2 equals negative 4 natural log of 2. And now I'm just going to divide both sides by this thing in this parentheses, the natural log 3 minus natural log of 2. And so I get that right here. X is negative 4 natural log of 2 divided by the quantity natural log 3 minus natural log of 2. If you use your calculator, you find that x is negative 6.838045. And again, that's an irrational number. So a good sort of rule of thumb in dealing with these sorts of equations, which often don't have nice solutions, is to keep at least 4 decimal places. So don't round too aggressively. A good rule of thumb is just to round to the 4th decimal place, 4th significant digit if you have leading zeros. And yeah, that's our introduction to to exponential and log functions, and particularly the natural exponential and natural log function, which will play an important role in things that we do from here on out. So there will be a homework assignment posted on that pretty soon. Right now, actually, my internet is down, so I'll get that up there and get this video posted as soon as possible. But in the meantime, stay healthy, and I will talk to you again soon. Y'all take care.